Good evening, all. Today we are going to cover the next point based on feature extraction. We have seen today some of the different techniques for how we can use dimensionality reduction process. So feature extraction is nothing but a small part of that entire process, wherein you can define when we are working on a very large amount of data in machine learning. So that much large amount of data coming into a real-time system can be very tedious to filter out. So what we do in feature engineering or in feature extraction here is we uh, take out the unnecessary amount of time and storage, wherein there will be a lot of input data which is obviously redundant. And to handle this large amount of redundant data which is unnecessary, or without having that part of dimension, extracting the necessary features only, keeping up its originality and its accuracy, we can achieve the same amount of you can say accuracy with losing some of the dimensions. So this kind of adaptation or this kind of approach towards the large amount of data, we call this kind of structure or this kind of can say process as a feature extraction, right? So it is a technique which is used to reduce a large input data set into relevant features. Only those features we will be selecting which are most important for our data set and which will be further can be used for our processing. Now, this is done with the dimensionality reduction, right? And here what we do is we try to reduce the different dimensions to transform our larger input data, as in your data set, into very smaller parts, or in terms of you can say as very meaningful groups, small chunks of data. Chunks means small parts of your entire data set. We divide it into different dimensions. This very large data set, provided directly raw or after cleaning or data wrangling, it still has multiple dimensions. So we can reduce those dimensions, and based on these reductions of dimensions, you can still have your data meaningful, which would be further used for processing, right? So feature extraction will help you to get the best feature from those big data sets by selecting and combining variables into features, right? Thus effectively reducing the amount of data. Now what we do here is we try to extract only those features which are very much essential, only required for our data set or our model to process, right? Rest other things we can exclude, right? We can extract it, we can leave it behind. That will not affect your accuracy or the actual data, right? The meaning will not change, it will remain as it is, the model will be performing, right? So what are these features? They are used for easy to process, which are still able to describe your actual data set. That will not change the meaning of your actual data set, neither it will affect your accuracy or the originality of your data set, right? If these situations satisfy your data set, then for this kind of concept of dimensionality reduction process, we can call here as it is a feature extraction part. Now let's take a very simple and small example, right? Now on the left hand side, what you're seeing is a bike, right? On the right hand, what you're saying is the different parts, right? These are your features which combinedly decide that this is a bike. Now there is a possibility if I apply some feature extraction algorithms on this kind of data set, which are having multiple features, right? Now what I need to do is I need to identify such features in a minimum form without losing any kind of accuracy or the meaning of my data set. Without losing these 2 points at least, I need to apply feature extraction, wherein with minimum features, I can define how your model can get input and giving the highest or more appropriate output. right? Now these are, you can see, a grid of 9 different features which describes your bike, right? So you are able to see that there are many, you can say, wheels are there, there's kind of shock absorber, there's back seat, there's, you can see, the front light, then you have the spokes here, then there's a fuel tank over here, right? So what are the minimum features I can find out from this kind of grid, so that my model could be able to identify this feature is of a bike, right? I'll needing the I can say wheels, right? One wheel instead of two wheels, one wheel, depending on the feature or the representation of that wheel, I can identify that this is a wheel for bike, right? The fuel tank I can identify, the front headlight I can identify. So what I'm doing is here I'm reducing my features, so that unnecessarily, if I take all of these features, all of these commons, and put it for processing, it will take more time, right? So what I do is I reduce those different dimensions which are unnecessary. Even though by reducing that, I can able to identify what the actual uh, uh, feature is, I can reduce those features, the unnecessary or the irrelevant data. Even though I can achieve it, this kind of technique of reducing your maximum features to a minimum part, wherein you are having a meaningful a group for processing, this kind of algorithm where we imply is a part of feature extraction algorithm, right? Holding with minimum requirements. Do not take all features and put it in your model, then try to process it. It will take a large amount of time, because in real time scenarios, there is very large amount of data coming on, going on, and we'll be having the raw data over there, right? So what we need to do here is focus only on the meaningful groups, right? If I want to represent a bike, what are the different features of bike and what are the minimum features of bike? Minimum in sense, without changing the meaning. If one of the important feature is missing and I'm not able to identify whether it is a bike or something else, then feature extraction won't help us, right? So reducing the meaningful dimension will also lead you or will mislead you somewhere else, right? So this must not be happened in feature extraction. Now, how it can help you while training a machine learning model, right? See, there are some can say good part, advantages and disadvantages of using this. Even though for any kind of model we have seen the concepts such as overfitting and underfitting, right? So over optimization will also lead or mislead to your model to go to reduce your accuracy. It will not perform well in testing phase, even though it has performed in your training phase. So such kind of issues might be raised in overfitting or in underfitting. Same possibilities will be occurring into your feature extraction. Now, what advantages will it give? If I'm going for feature extraction, it can lead to boost in training speed, because I'm having, you can say, minimum features without losing the originality of my data set. It can still identify what kind of data set meaning I'm having. So it can increase my training speed. Second, it will improve my model's accuracy, right? Because training speed, as it is increasing without losing any features, even though by reducing the dimensions, I'm improving my model accuracy. Third is reduction in risk of overfitting, right? If the features are less and my model's accuracy is still the same achievable as that of with more features, so automatically my risk of overfitting is being reduced, right? Because already less important, unnecessary or irrelevant data is already reduced. So no issues of overfitting here. Now, rise in model explainability. Whatever features we have taken by reducing the dimensions are the most appropriate, most relevant data which describes your data set. So obviously your description of your data set will not have any irrelevant data, right? You do not have to drop any columns. You do not have to search for such data where there are null values, where there is not a number value. Such kind of dropping or slicing will not be there in feature extraction because that has already been done. And based on these features, what you have is the better data visualization with less number of features and good model predictions. Less number of features will give you and will try to focus you on the exact features where your model will be giving you the best fit line, right? So these are some of the, we can say, advantages of using feature extraction. There are some techniques we'll be seeing how feature extraction can be implemented into your machine learning models. Now, where can I apply these? There are some applications wherein feature extraction can be applied. As first is the pattern recognition, right? Image analysis, we have pattern recognition themes. So in this way, what we do is we try to analyze the different, you can say, patterns, trying to match one with the other, and then try to compare the results and then give it the best optimization models. Very best example you can say is for image processing, because there are lots of concept based on OpenCV, that is open computer vision. So computer vision basically deals in real-time systems, as in if you're opening your mobile's camera system, then whatever it sees is it tries to read. If you try to capture the data, every pixel will be stored in terms of your binary 0 or binary 1 in terms of an array type structure, and those numbers will represent your image, right? So a little information about how image processing is done. Whenever you click a photo from your mobile phone, you have a resolution, right? Suppose it is of 800 by 600. So 800 by 600, that is 48,000 pixels are generated at a single click, and that much amount of data is stored onto your mobile phone, wherein if you're having a color image, each pixel will hold 3 different values representing a color, right? If it is RGB, so it will be red, green, and blue. So either of this, you will be having slight difference between red, green, blue, yellow, and different colors representing your whole image. So each pixel will hold a value. You can see how much large amount of data would be there. So if I try to convert my image into a black image or a black and white or a grayscale image, lots of other dimensions, right? Even though I lose the color of my image, the meaning does not changes of my image, right? It is still recognizable, right? If I take a photo of myself in color and then try to convert it into grayscale, right, I will still be identified as a person, same with of color photograph, right? So but I reduced in my other dimension, but still the meaning is not change of my data set. In same way, feature extraction works. Bags of words, there's a concept in NLP stands for natural language processing. What happens here is there's a concept as a bag of words. That means there are all vocabulary, dictionary words are being stored in this library, and this library helps us to identify what kind of sentiment is hidden behind that kind of word, behind that kind of sentence or written in a paragraph. What does a user feels about it, right? So basically, for any kind of sentiment analysis, we use natural language processing applications, and one of them package's name is bag of words. So in any social media platforms, wherever you put a smiley, you reply to a post, you write something, those are converted and compared with bag of words, and then try to analyze what kind of sentiment is having to that particular post which you have replied, right? And there are different auto encoders in unsupervised learning, right? So see, these are some of the applications which are being applicable for feature extraction. Then let's see some of the techniques, because from this techniques we'll be going to see the PCA technique used in feature extraction, that is called as principal component analysis. Some of the features are, firstly we have PCA, the principal component analysis. Second is ICA, that is the independent component analysis. Then we have linear discriminant analysis and LDA. locally linear embedding, LLE, and the last one is the T-distributed stochastic neighbor embedding, right? So these are many, you can say, techniques, but most common and most famous technique and very easy to understand, learn, and implement is nothing but the principal component analysis, right? This is the best technique used for feature extraction.